I'm happy
ready?
to introduce. I mean, I don't know how much I can say, but it's very nice to meet you. Phuc Minh is
Okay.
our first speaker today, and yeah, look forward to your presentation.
Thank you. Yes. Uh, okay. So we can start now.
Yes, let's get started.
Yeah.
So you have 15 minutes, around 15 minutes to kind of give talk, but we can also have more interactive session in the middle.
That's okay. Uh, Hello everyone. Today I will present our latest work called the reasoning boundary paradox, how AI constrained language model. So this work is a collaboration between the university and University of Notre Dame. Um, large reasoning model like DeepSeek R1 or Kimi 1.5 have recently shown remarkable capabilities in complex logical tasks like mathematical reasoning or competitive programming. And prior work, they believe that reinforcement learning with verifiable reward, often termed as RVR, is the main success behind achieving these remarkable capabilities. So for each problem, you allow the LRMs model to generate a detailed reasoning trace and the final solutions. And we will have a binary reward function that indicate whether the generated solution is correct or not. And by optimizing this binary reward function, DeepSeek R1 can achieve like nearly 80% accuracy in difficult mathematical reasoning benchmark like AIME 2024. But however, recent work they question that really does RLVR really expand the reasoning boundary compared to the base or pre-trained models. So they define the basket metric as a measurement of the reasoning boundary. So the basket metric will tell you that the likelihood that the model can generate the correct solutions if we only allow the model to produce K trials. So when the K is small, the RLVR model can consistently outperform their base counterpart. But as we increase the K to a large sampling budget, like 64, 1024 response for each of the problems, they found that the base can catch up or even outperform the RLVR models. So this creates a phenomenon that they call coverage shrinkage, where the IVR models tend to show less problems compared to the base counterpart and under a large sampling budget. So in this paper, we try to understand why this phenomenon happened and how can we mitigate this issue. So at first, it's useful to contrast what is like our goal in expand the reasoning boundary in LM reasoning compared to traditional RL. So in traditional RL, we usually have like define where define a single and verified Markov decision process, and our goal here is justify an optimal the optimal policy for that single MTP. But in the case of AM reasoning, each problem can induce its own MTP with a distinct and unknown reward function. So by using the basket, we want the LLM models to solve more and more problems. This means that we want the model to find the optimal policy for how many MTP can the AI model can solve. So this raises the question that if we learn to solve find the optimal policy on a problem is, how does this affect to learning on other problems exam during our VR training? In this paper, we will utilize the learning dynamic framework by we will use the plus step influence to analyze how the model prediction as measured by the log probabilities of the problem and solution pair change after an update step. So based on the per step influence, we will define two metrics. The first is the interference, where we measure the influence of an update on correct problem and solution pair generated by an off policy. We denote this as mu here. So throughout the paper, we will use the base model as the behavior policy to quantify how the model prediction change and the bit throughout the IVR training in the initial correct solutions. So the second metric we use is the relative strength of an update step, which measure how drastic the model change after one update. So if the more drastic, it means that the training data have very high influence on other outside training data. So for this experimental setup, for the training data, we will use the deep scalar dataset, and for the models, we will use two model family. The first is the Fan Superfly and Llama 3.2 models, and for the benchmark, we will use for benchmark AIME 2024, 2025, Mach 500, and Minerva. And we also construct a problem dataset where for each problem in the training data, we generate the response under the base model to calculate the interference and the relative strength in model prediction outside the training batch. So our first finding is that throughout the training process, the RIVL model can consistently improve the accuracy as measured by the batch one in the first figure here. But it comes at the cost that the model start to suffer from coverage shrinkage, where the batch K256 it starts to degrade over time. So along with the degrade in the coverage shrinkage, we also observe that both the influence strength and the negative interference grow during training. So it means that there is a negative cross interference between learning on the training problem can affect all other problems outside, like the test benchmark here where the model consistently degrade the log likelihood correct solutions under the problem data. So to understand how does the increase in negative interference can be seen as an indicator of the correct shrinkage, we also measure the correlation between how the basket change at each intermediate checkpoint and change in the negative interference. So we observe that there is a very high correlation across different four benchmarks. So it can be seen that the increase in negative interference might be a factor that lead to the coverage shrinkage. So this can create an effect we term that a winner take all, where it means that the existence of negative interference can cause the model to only focus on improving on a subset of problems. And while improving on this subset of problem, it can cause a regression on others that we cannot control during the training batch. So to understand like which problem is the winner and which problem is the loser, we also provide a perplexity analysis where we measure the perplexity of the model pi under the policy distributions mu here. So first we will use each intermediate checkpoint during our training to generate samples and see how the log likelihood under the base model change throughout the training. So we observe that most of the generated response are so increasingly high confidence under the base model. So it means that the RVL model just tend to generate really high likelihood solutions under the base model. And we also observe that for the initial solution and problem solution pair that generated from the base model, the RIVL is a bit reduced confidence under those data, even if those data is correct as measured by the orange curve in the middle figure, where the perplexity consistently increased even if those solution is correct under the base model. So it means that so to understand that which problem like are the winner and which problem are the loser, we also define a metric we quantify for each problem. We see which problem that the IVR model improves and which problem that the base model perform better initially and or decrease over time. So so we create a two data set for the problem that our VR model improve and for the problem that our VR model decrease. We observe that most of the problem that the VR models increase already have very high likelihood to generate the correct solutions under the base model. But for the solution that the RAVR model decrease, it is a bit very low likelihood to generate initially under the base model. So it means that the RAVR model only incentivize the problem with very high, with already high probability to generate correct solutions under the base model. And okay, so to understand what really caused this phenomenon, we also try to analyze this phenomenon using like a simple bandit problems, where we have an optimal actions y plus here, and we will analyze how the gradient of on policy algorithms reinforce causing this phenomenon. So the main concept in the on policy algorithm is the introduction of a new weighting mechanism that simulate the sampling process during the RAVR training. So when those tokens receive very high likelihood, we usually have very high magnitude, high gradient to update. And for the actions that achieve received by very low likelihood, it's very hard for for the update to change the model predictions as a waiting term. He had very low likelihood. So this cause a problem that when there are three multiple correct actions, then the one with the highest likelihood will dominate the learning signal. And if we just only learn to improve the one with the highest likelihood and degrade the likelihood of the other one, even if the solution is correct. Another one, we observe that even if we employ the negative gradient, which can increase the probability of all other actions, but the one that increase the most is the one with the highest likelihood tokens. And if the correct action lie in the low likelihood region, then the improvement is negligible or even decrease, and the one with the highest mode will increase only. So moreover, we also observed that during training, the RIVL model can start to lose the ability to generate different reasoning behaviors. Like the Quen superfile, we observed that it can generate the code reasoning behavior. So for each of the problem, instead of just thinking step by step in natural language, the model can use pattern interpreter to define mathematical functions in pattern and output the final answer. So usually this behavior can achieve decent performance initially. So throughout the training process, we observed that this code reasoning behavior start to lose the model start to lose this ability over time, and the natural language start to become the dominant one. So this can be explained by the fact that in the training data, the natural language usually have the initial higher initial accuracy. So the LLM model just try to incentivize a better strategy in the training data. But of course, this can cause a problem for the problem where the code reasoning might be better, especially in the minimal benchmark here. We observe that the code might be perform much better, and it also explains why the IVR model perform not very well in this benchmark. So moreover, we also show that the current regularization in IVR cannot prevent the negative interference in terms of the reverse scale, where it provides little to no penalties on region where our IVL model will put low probability mask on because of the mosaic behavior. Another regularization technique is the clipping, where we also observed that the clipping mechanism can enforce an effective judge region in the training data only. But outside the training data, it has little to no influence, and the judge region variations start to increase over time. Showing this it is still ineffectiveness in mitigating negative interference lie outside the training data. So
Sorry, quick time check. So
yes.
wish to.
So based those our observation, we use the response as a measure of problems that are highly solvable, and we only focus on problems with less solvable by solving on the problem that the ready response failed, and we also replace the reverse KL with a forward KL to enforce a more masculine behavior. So we observe that our method can consistently outperform the RGRBO in large sampling budget and even can outperform their base model. And we also observed that it can provide compatible performance in terms of the pass one metric. So overall, we review the negative interference phenomenon and why and show why the IO model only concentrate on solving the smaller set of problems. And we also explain that this to the effect on policy, and it will neglect the problem that initially low likelihood of correct solutions. We also propose have just a simple data correction that learn only on problem with low likelihood that is effective during our training. So yeah, thank you for listening.
Thank you.
So do you have any question? Feel free to ask.
So in the audience, you can also raise your hand if you wish to ask questions. And quickly, I was also kind of trying to figure out what pass at K actually means. So maybe that's a basic question.
Yes, so let me go through it. So this means that so for each of the problem, you prepare the model with generate like K solutions, and you will measure what is the expected likelihood that the model can generate the correct solutions within this K trial. So when K like go to infinity, then it's kind of like the model can generate any response, and the pass K will be equal to 1. So it's kind of like measure how the correct solution in the model lie in the which region of the models. Sorry.
Okay, I'm still struggling. So maybe in the formulation, maybe we can focus on the formulation. I don't see X in the expression, and I don't see C defined anywhere. So I guess N is like the number of samples or something like that. So can you explain like what these terms are?
So this means that for each of the problem, so you can generate n solutions. N might be larger than the K. So based on this n solution, you will estimate the pass K metric for the K lesser than 1. So initially they found that this estimation have cheap lower variance compared to just like sampling K trial and measure the expected accuracy when you just use K trial. So it's just a better estimation of the pass K metric. And so sorry for the typo. The pass K actually depend on the problem. And since I take the expectation over the data.
Okay.
Just to give a very quick intuition there as well, is the PassFK is essentially just the probability of sampling a correct answer within K trial of the language models. So,
Yes.
so
Okay.
if it's actually going to infinity, K going to infinity means that you know, you're more likely to sample a correct answer. So it's gonna like approaching one basically.
I see. Yeah, now I see. Okay.
Right.
Okay, that's a simple metric. Yeah.
Yes.
Mhm. But do you compute this analytically, like in this formulation, or it's not an analytic formulation? It's more like you sample still, right, from the language model.
Yes.
Yes, we still
Yes.
sample, but translation we can compute it analytically.
Okay, yeah, that's interesting. And you're saying the likelihood of reaching a correct solution is so why is that a main metric that you're looking for, right? Because I think your point is that when you train with this verifiable reward, right, then you are kind of favoring some of the solutions or path that had high likelihood initially. You're kind of rewarding them a little bit too much. So
Yes.
you're gonna be more diverse in your kind of reward scheme. Is that the main message?
So, I mean, the main message is that for the problem that the base model already know, then it can generate like very high likelihood of correct solutions. And so if negative interference happen, so if you keep learning on to increase the high likelihood correct solution, it can cause a decay on other problems that might not in the training data. So it can cause the model become less and less likely to generate solutions, correct solution on other problems. So because the basket take the expectation over different problems, so learning on one problem actually can have negative effect on other problems, causing a decay on the basket. So,
Okay.
yeah, so I think that is the main message of our paper.
So another thing that I like to add as well is that this PassFK is essentially indicating whether the model has the ability to solve a problem or not, right? Maybe the sampling would not recover it very easily with PassFK1, like within one trial, but the answer is somewhere, right? So it knows how to answer it, like if you do it like many times. And the fact that the RL trend model is having the decrease in PassFK, it means that there's a lot of problems that the base model, the RL trend model couldn't answer, but the base model had the answer. So it means that you know, like there's some sort of like coverage shrinkage, and that's is essentially something that the community is trying to understand why. Right? So the NeurIPS paper that you know, we put there as a reference as essentially receiving a perfect score of 6 you know, this year, and so this is a very interesting phenomenon. But our paper is essentially the first one that tried to explain why this happened.
So I guess my question is, do you see different trend when you switch your metric from PassFK to PassFK1, for example? Oh yeah, that's what you're showing here, right? In Figure 2. So they're crossing each other. Oh, I see. Because I guess then the problem is that eventually your metric, like all your evaluation and your reward model, these are focused on a single kind of sample.
Yes.
And,
yeah, a subset of problem basically.
I see.
It's probably more correct. Yes. So it can solve a subset of problems very well. but there are a lot of problems that it couldn't solve, and the base model already have the solutions if you increase the K.
I
Right.
see.
So
Okay, yeah, that's fine.
it means that this creativity in problem solving of the RL train model is losing this ability after you do RL training. So essentially, if you think about like one problem with like multiple different ways of solving it, like over time, the base mod like the RL train model is just like collapsing into one way of solving it. So you still
Yeah.
can solve that
Okay.
problem very well because passage one is good. But if you go to a similar problem that may require like, like solution two, for example, it's not going to work because it's losing that ability to use the second way of solving it. Right.
Oh,
And
wow.
that's essentially is not reaching the potential of doing RL training, right? Because we expect to when we do RL training, it's gonna increase the ability to solve more and more problems that are not on the training data, but it's not the case here.
Thanks. So this is quite insightful, and I wish to continue the Q&A afterwards in Slack actually. That'd be
Yes.
great. I have a few more.
Happy to answer, yes.
Yeah. But now I think we have to switch to the second speaker of the day, Marcus. So how it works again is, the first speaker will be introducing the second speaker. Are you ready for that?
Thank you so much, and Phuc, congratulations on this great work. I actually have been reading the paper and studying it, and so it's nice to hear you present it. So great job.
Thank you.
So yeah, so as you said, so June, thank you by the way for organizing this. I think it's great to have this forum to exchange ideas really across different disciplines and labs and countries, and I think really wonderful forum that you're putting together here. So my work really, as you said, has been on using AI for science. I've come sort of from trying to figure out how to model discovery for many years. I'll give you a little bit of background on this, and then I'll show you the particular paper that you invited us actually to present on, which is this paper. I think that's the one you found in arXiv, which is one of several papers we've released recently on using AI systems for discovery, especially in material science, but also in other areas. So this is actually all work done by my postdoc, Alevisa, and I don't know if he's here, but he is the first author of this paper, and I'll show this particular paper later on in the talk. Before that, I'll give a little broader introduction into the topic. But yeah, it's been an exciting time. My lab at MIT, since many of you probably don't know my work here in this audience, but I'm very interested in of course, material science and chemistry and biology. That's sort of my scientific domain. And I have been fascinated with building computer models since a very long time ago. I did my PhD actually at Max Planck in Stuttgart, which is now called MPI for Intelligent Systems. So some of you, I think, know that, and June and I just talked about this before we started. So I built models of materials and physical systems. I usually go across scales. So I'm interested in connecting the molecular scale, which you see a little bit here on the right, all the way to the macro level. And I use various kinds of models for this. And in the last, 10, 15 years, we've become really interested in, creating more abstract models that really connect between different systems of interest. And that's how we got interested in AI for a while. And I sort of followed, of course, the history for a long time. And I think, one of the, statements I usually start off with is to say that there are a lot of problems where we have been able to show pretty good advances in solving problems. And of course, there are other famous examples like AlphaFold, but, maybe playing games or math problems. And even benchmarks, of course, you see a lot of advances in saturation of these. But the kinds of problems I'm interested in are different in nature, which is they're, really open-ended problems for which we don't necessarily have an easily verifiable solution. So a lot of the techniques that actually, Phuc, you talked about and others have used, and RL proper, like in Go, AlphaGo, are much more difficult to apply because we might not know, or usually in scientific discovery, we don't know what we're looking for in the first place, right? So there's a lot of really open-endedness to this, not only in having verifiable solutions, but even asking questions or formulating questions, right? So a lot of this building these systems really becomes becomes a challenge of how do we build evolving AI models that can you really update their beliefs about the world as they solve the problem. And I think that's a theme that we've been seeing in our work in the last few years, and I think the community is also embracing pretty intensely right now, as we've seen in the last couple of days, even with announcements of new labs being formed and things like this. That we got to change the paradigm from just training models on data to really have much more agency in interacting with the world. In our case, the world means material or chemistry or biology, and there sort of have to be very flexible ways of getting signals about how the model can better understand what we're trying to discover. And that involves also finding out what are the right reward functions or loss functions we want to use. So it's sort of very open questions right now in the field. So it's an exciting field for everybody getting into this. I think AI science is probably one of the really current frontiers that are extremely valuable to explore because they're pretty much unresolved, I would say. And here's a couple of examples of why this is. I think I'm really interested in, as a scientist, I do work in sort of both the reductionist area. So I want to maybe distill very complex behavior into, scaling laws or an equation or an operator or PDE. On the other hand, I have, creative outputs where maybe as an engineer, I might design something, or as a creative, as an artist, you might create something new. And I think both of these principles, reductionist sort of AI models telling us, okay, here's the scaling law that governs the system, or here's the equation that governs the system. Or on the other hand, systems actually create something totally new. It's really hard. And I think that's where a lot of the current technologies and methods really end. And yeah, I think actually, if we think about building models for these purposes, I think there's some guidelines or guidance we can actually get from this thinking. And we don't necessarily want to put too much the human perspective into this, but at least we can maybe get some guidance on how we can construct maybe reward functions or other types of objectives, how the models should look at the world. And one of them is we have to have both the reductionist principle and understanding compositionality. So we have to be able to construct solutions to complex problems, and they have to we say this mathematically in a sense that we want models to be able to understand the differences between, what are the things we can generalize about a system and what are the things that are different between different systems and why. And the objective function we're using really is that we want to not understand all the reductionist principles always, because systems cannot always be reduced to reductionist principles only, but we want to be able to organize the differences and understand the differences. And so a simple example for this is actually a PDE, where you say, oh, I have a PDE that governs 20, 30, 50, 100 different phenomena, from fluid mechanics to solid mechanics. But there are differences in how the boundary conditions look like, or initial conditions look like, and those are differences. And so by understanding how you get from a phenomena, how you get to explain a phenomena using sort of principles that are shared and principles that are different, you identify true sort of understanding of a system, even though there are differences between the different outcomes. And that objective, I think, is something that we got to build more into how we construct AI models for science in particular, but I think beyond as well. And as I think the previous talk nicely showed, there are some really interesting surprises and questions, and actually open issues and how we train even sort of modern reasoning models and what the limitations are. So really exciting field. My world looks at materials, right? So these are really complex systems. People started modeling them in the 1950s when we had big computers by atom statistical mechanics. We then moved on to build models that were more different, more complex. I mean, we went from metals and solids to proteins, and you have seen, the last couple of years, actually, there were several Nobel Prizes given for this kind of work. Early on, we had a Nobel Prize given for modeling proteins. This was, I think, in 2013, Martin Karplus and Mark Levine and others. And then recently, of course, Nobel Prize for, applying machine learning or deep learning to predict, protein structures and design proteins, right? So this, is a nice illustration, really, how this field has changed and has been enabled by computer simulations. And I think we're now at a point where we're beginning to model the discovery process itself. So in the trajectory of my own work that I've done, moving away from a single system to understanding a lot of different systems. And let me explain why this is important. I think if you look at a material, like, for example, one of the things I work on is silk or proteins. It's a fascinating material. It's stronger than steel, for those of you who are not in the field. So if maybe get you excited about that material, it's a fascinating system. It's obviously totally biocompatible. You can eat it, yet it is stronger than steel. And, silk is extremely complex. This is a structure of a spider web that we have scanned. We have a lab here at MIT where we scan 3D spider webs and digitize them and make them into models. And this is sort of moving through the spider web in space. And you can see enormous complexity in there. I mean, you're going to see this pop up very soon. There's actual structure in there. There's a organization that is not random, obviously. And the question is really, if you look at this enormous complexity of billions and billions and billions of atoms, different kind of proteins, different kind of processes, how do we organize this knowledge? And that became a passion, or I would say an obsession of mine, actually. And that is, how do we really understand physics or chemistry, biology? And it's not that we are understanding every single atom. It's, when I give a talk about, let's say I would give a talk about spider silk, I would tell you about relationships. I would tell you that there are certain atoms, certain amino acids that matter more than others. And I will tell you about the patterns that make a strong spider silk. And I would maybe tell you about the processes that make it happen. And, this kind of very effective condensed abstraction is the way scientists think about the world and how we communicate, actually, between each other. And so the question becomes, how do we model this in using mathematics? And so 10, 15, or actually 15 years ago, we started building models of these translations using category theory. And we found this to be a very effective method to do, building essentially relational models of how a system can be described as a mathematical concept, but also how different systems can be related to each other. And this is where the idea of differences and similarities and comes in, because categories allow us to build functors, and those functorial mappings allow us to understand when the mappings end and how different systems really relate to each other fundamentally. So it provides a mathematical language to do this. Now, this kind of work we've done back then, we did manually. And what I mean by that is we basically used human intelligence to write down these relationships. Okay, so we couldn't discover them using simulations yet. It required the human mind to create the abstractions. And math was helpful in organizing our thinking, but we couldn't scale this to a point where we can actually use this to fundamentally make discoveries. So that's sort of dormant in my drawer, if you wish, not really, but in my drawer in my desk, basically, to set in there. And I kept working on it and thinking about it. But 5 years ago, so we began to actually see that actually this kind of methodology could become important, because we had at the time seen some really interesting advances in, of course, graph neural networks being used in a lot of different cases, including for protein folding, but also we've seen that, and this is the most important advance, probably the most important concept, is that we've seen that, excuse me, some of the early work on transformer architectures, to me, looked like, a methodology that allowed us to break the problem into a graph forming operator, which is essentially a attention mechanism, and a computation on the graph, which is the GNN architecture. So this was sort of my focus, actually, on transformers and why I thought they're interesting. Okay, and at least as a tool in creating intelligence. And the reason you can see, because in a category representation of a material, you got to find essential representations of patterns, and you want to then compute on them, think about them, and think through them. And so this has guided a lot of the work we've been doing. And actually resulted in also us to think about efficiency and how do we create models for discovery, which I mentioned earlier, have to be able to adapt themselves, and how do we implement this? And I think there are a couple of sort of pieces that came together over the years that made it really possible to do this. You might know this, actually, this is work that was done in the 1950s and 60s, early AI, using these hard-coded intelligent systems, like mycin was an example, and many others. And we have seen actually that if you combine neural networks, which has been the paradigm for the past 30, 40, 20, 30 years, with these symbolic approaches, you can create, I think, a much more powerful intelligence. That's the thesis behind the work we're doing. And you can see why, probably because, of course, a symbolic representation of a system, like in a category theory, is powerful, but it is not differentiable easily. And to us, neural networks are a glue that connect different symbolic methodologies to each other. And that's the sort of the problem we're working on in developing algorithms to apply this to scientific problems. And yeah, I mean, you can see on the right-hand side is a model we've developed called Prod Agents, which is a self-organized multi-agent system to solve really complex protein design problems. And actually using sort of the self-organization principle that, of course, we have studied for many years in biology, right? So a lot of these biological systems, whether we're talking about silk, whether we're talking about cells, they all rely on this, loop of feedback and adaptation. So a biological system is not built or trained and then used like kind of like engineering systems. So like if we're building a laptop, right? My laptop is in front of me. Apple designed it and made it, and it doesn't really change itself, at least the hardware, right? Whereas in biology, the hardware of life, really adapts all the time, right? So you can see this in bone, you can see this in cells. These are all things I've been involved with over the years, studying cell differentiation for smooth muscle cells, all the way to bone mechanics. And so these systems evolve. They're not made at the point they were conceived, but they have sort of the innate ability to change. And they do this through feedbacks and signals. And so the question, I think the previous talk also really nicely highlighted, is it's all about, how do you design the system to do this well? So that becomes the design objective actually for us a lot of times in these models. It's not so much training the model and then letting it sort of become perfect and magic to happen, in quotation mark, but rather, how do you design a system to be really responsive to signals? I mean, rewards or penalties about the behavior. How can it adapt well? And I think the previous talk, I think, nicely illustrated this as well. And what it means for discovery or predictions, we are very interested in sort of these compositional steps. So we want to know, how do we realize true compositional reasoning? In other words, truly novel insights. So I don't want AI to just tell me what has been known before, because in science we want to, of course, discover new things. So the question is, how do we do this? And I think one of the sort of really big themes we've seen is, of course, emergence. So you have discrete elements that are somehow communicating, and they have bottlenecks in communication between them. So they have a sort of an ability to learn or develop some sort of language, but it's not all information is shared between every entity, right? We find that sort of reinforcement learning is generally a good direction, we think, because it allows us to move away from memorization, let alone, of course, that most problems, like the unexpected or never before seen, right, phenomena, we do not know any kind of training data, right? So you can't train the model. And I want to put a point on this. If you're looking at, let's say, AlphaFold, it is trained on all existing proteins, but those are only the proteins that nature has made and that we have crystallized or analyzed, right? There are many, many more proteins that we've never looked at. So in discovery, whether you're discovering truly novel proteins that are really out of distribution, or whether you're just discovering new scaling laws, I mean, we have to use different methodologies. We can't rely on the conventional training paradigms. We actually have to build in the ability to discover and update the model of the world model, as we're solving problems. So that's a thesis behind the work. And now I only have, I think, maybe 10 minutes left. So I'm going to show you a few examples of what we've done within this framework. So one is, this was in 2023. And I think in the scientific field and maybe others as well, was one of the first sort of real multi-agent implementations we've created. We created at the time using GPT-4 as one of the foundation models, a system that could solve a scientific problem. So this is sort of the early proto AI scientist, if you wish, back then. And what we did is basically we created a system that wouldn't answer from memory, but it would actually write a program or code to generate data using first principle simulation. In this case, was DFT, density functional theory, to basically create this own data set to then train, in this case, a regression model to then give us the answer. And for me, this is this is a simple problem, but I always show it because I think this is for the folks in the engineering community or science community, I think they're insightful, right? To see this is a paradigm where we can teach models to not just remember things, but to actually create a strategy to solicit data from whatever means there might be. And that could involve experimentation, it could be autonomous experimentation, it could be first principle simulations, could be retrieval from the internet. I mean, it could be a lot of different things. And so the idea is that you want to have an ability for the model to update its understanding of the world. And that's the key really behind it. And so from the early examples, we went on and did a lot more useful things than just predicting the energy landscape of molecules, which is it's not useless, but it's a small problem. So we went on and built really complex agentic systems this was in 2024, that could design proteins. And the component here, this is also work by Alevisa, my postdoc that I mentioned earlier. In this work, we actually were able to integrate not only generative AI like Chroma, OmegaFold, AlphaFold, Force GPT, which is a GPT model we had trained to design proteins, but also physics simulators. And the exciting idea here is that you can get signals about the behavior of a system that is multimodal, multidimensional. And so as this model thinks about the problem and it can make predictions and solve problems, it can reason over all these different dimensions of what makes the protein stable, what makes it useful, as opposed to a single model, generative model that gives you just a sequence or a structure, and then you have to figure out, is it actually manufacturable, is it toxic, and things like this. So this theme of multi-agent systems, I think, is very promising, and as you know, in the last couple of years, it's really taken off. I mean, we have sort of spawned a whole industry, if you wish, even of companies and startups that sort of using this approach now. There have been attempts also in other areas. We have published in our lab bunch of different applications in alloy design, which is metals, so they're very sort of more engineering materials. And we've also applied this technology in a recent paper called Sparks to discovery. And what that means, the difference to the previous examples was we've designed an alloy or a protein, but what we really got to do, of course, as scientists, is to discover principles. So I mentioned earlier, so the reductionist idea. So this model, Sparks, its objective is to sort of really explore and understand the world and create the most general model while understanding the differences. And so this is sort of the penalty is essentially, if the model can understand the world and its differences, we're happy. It has to be a broad coverage model. It has to be as simple as possible, but it doesn't have to be universal for everything. And again, as I said earlier, the boundary condition would be a great example for a PD operator. And we penalize any kind of unorganized differences. So things that the model doesn't understand about the world will be penalized. And this strategy actually works really well. So we can, the model will self-organize, the agents will plan, execute, and compute forever, in quotation mark, as much as compute you have. And they build a sort of an improved, better understanding. Like in all AI science, all the AI scientists sort of methodologies, I think ultimately end up, the models can write a paper, of course, and there's many examples in our work that we have published. The key thing I want to mention here, what Sparks can do that other multi-agent systems have not been able to do, is that we actually deduce actual scaling laws and actual principles, and this is very important. So we don't just say, here's a prediction. We can understand trends in the data, and the data is all generated by the model itself. So there's data that the model will seek out in the world, the internet, through measurements, through simulations, but it's not provided by the user. So this is entirely self-explored, which is really the key here. And then the last example I want to show before we're out of time is this work that actually that you invited me to speak about, which is using this kind of Sparks architecture to model or design inorganic materials. And this is an area I think that's been very also hotly debated and hotly explored. There's MatterGen, which Microsoft released a couple of months ago. And there's the Materials Project, which is the database. And by looking at these alone, you can see the weaknesses in either one. So the Materials Project is just a database where people deposit existing data, right? MatterGen is a generative method that can design a new material, and in this case, inorganic materials. But you have really no idea whether these materials are manufacturable, whether they're really novel, right? We have to test that. And so what Sparks Matter does, essentially, it puts this multi-agent systems to work to validate predictions in all different dimensions, including manufacturability, physical stability, novelty, and so forth. And they become much better than any of the surrogate models alone, or any of the databases alone, or any of the LLMs on their own. And you can do some really amazing stuff. So I invite you to take a look at the paper. It's on arXiv, where we have shown that we can design truly novel materials, meaning they have never been seen before and have been studied before, but they are physically stable, right? We can validate using density function theory or molecular simulation to show that these materials actually are stable. So they are novel. There's reasoning from the literature. Obviously, these AI scientists, they can go out and look into the world and compare with existing papers. So there's a lot of really rich reasoning going on behind it. And can design materials that are real. There's a couple of different examples in the paper. One is thermoelectrics. This is another example that we had is a toxic-free perovskite oxide model. It's a material. It's a particular class of materials that are used for energy conversion. And among the quadrillion or gazillion possibilities, right? You want to kind of find true novelty and stability, and you want to do all of this automatically. So this is the kind of work, that I'm going to give you a perspective that in my lab or in other labs, PhDs would have done 2 or 3 years long. 5 years, they would have spent the time running simulations, comparing literature, predicting a new compound, assessing stability. We can automate this entirely now. So Sparks Matter, our model, will do this in a couple of hours to days, depending on how much compute we throw at it. And does a really good job. So last thing I want to show is, what's going on under the hood. I mean, what are the sort of the underlying architectures? One of the things we've spent a lot of time on are compositional reasoning models, where we don't just let models reason in natural language. And I think, again, the previous talk, I loved it. I think made a point that if you let models reason uncontrolled and you just give them rewards, which they can somehow achieve, but not necessarily structurally sound. I mean, they don't generalize, in other words. We've been looking at building reasoning models that think in categories. So I mentioned in the very beginning, category theory. So this is an attempt where we build reasoning models that actually do structured thinking. And what this looks like is sort of like this. They think about the world in relationships, abstractions, and actually even logical expressions. You can imagine this to be a graph representation of a task and a symbolic abstraction, even first-order logic, all the way to design principles, hypotheses. And so this is a much more structured way to think about problems. And because these, all the reasoning traces end up being, can be shared in their representations and how relationships look like, a model can generalize much better. The other advantage, of course, of having compositional reasoning in the reasoning trace itself is that we can very easily use multi-agent systems. So we have a reasoning agent, and we have maybe a verifying agent during inference. So this is not during the training necessarily. This is during inference, where the second agent can correct errors, right? So every single compositional step in the reasoning can be assessed and can be validated or falsified, right? So this provides us with the ability to build models that can, think for a very long time, and every thinking step can be, mechanistically traced and verified. And so here's an example. So the way the model will build its own representation of the world, with or without external verifiers. I mean, this could be informed from measurement or data. So the model kind of builds a representation of how this problem is best assessed. It thinks about all the different dimensions, all the different facets. And because we're thinking in graphs, we're no longer just accumulating pages or thousands and hundreds of thousands of tokens in language. We actually have a small world representation of the world, no pun intended, which ultimately looks like this. And so we basically get a representation that, you know, can be verified internally, and it's extremely compact. So this is, I think, the direction that we were very excited about in building reasoning models that are graph native. We call them graph native reasoning models, which have a lot of course, you know, associations with how physicists, material scientists, chemists, biologists think about the world. And but of course, we don't prescribe the detailed mechanisms. You know, we let the rewards you know, decide on sort of, we let the model decide how the policy evolves essentially and how the thinking proceeds. But we found this to be quite useful. And so, yeah, so I think this is an area, I think we, you know, I think we're out of time, but we can think about creativity. You know, we can do reductionist reasoning. We can also use these very rich representations in doing exploration much more effectively. And in fact, one of the you know, sort of secret powers or the superpowers of Sparks, the model Sparks model, is in fact that we can create very high degrees of exploratory measures. You know, in science, and I think the previous talk also nicely showed that, well, if you let the model sort of get to an answer well enough, you know, you end up being, the model is happy and it sort of focuses in on this, but it doesn't actually understand how the broader world looks like. If you're able to, you know, formulate new hypotheses very well, you can teach the model a lot of different ways. So this comes back to, I think, how do we create, you know, signals for the model to think out of the box? And again, these graph native reasoning models, I think, are very powerful for this because they innately allow us to construct hypotheses that they've never been seen before in the training distribution. And so we really teach the model, you know, to learn something new, which is, I think, the reason why, of course, Go, AlphaGo, and others work well, because we were able to explore reasoning traces that are totally outside the training distribution. And that's something that I think we're missing with a lot of language model RL methods right now. So as you can tell, I'm a big fan of that work that the previous presenter talked about. And I think it connects with some of the things we've been doing. And yeah, hopefully it'll be interesting. And so we kind of, yeah, really try to push these AI models to become, you know, to be able to teach us something new as opposed to us just retrieving stuff, which is great. I mean, I think ChatGPT is amazing because we can retrieve a lot of stuff that we have never read about, and we can let it explain to us. But science is a totally different level, of course. You know, in science, the scientific discovery, we want to find things that have never been seen or talked about before. And that's been the focus of my lab in the last 15 years or so. So thank you very much.
Thank you so much for the great compact talk. We should have invited you for the full session, actually full hour, I think. It's a lot of materials and I learned a lot, and I have tons of questions, and I presume a lot of the others will also have tons of questions. Unfortunately, we don't have time for that today. Marcus, would you be willing to kind of join the Slack space where we can ask questions asynchronously, and maybe you'll be able to ask the questions?
Yeah, I have to. We have to figure out the mechanics of the Slack, because the email I gave you, I couldn't accept the invitation, but that's something separately. Yeah. So yeah, absolutely happy to do that. Yeah, we'll continue on Slack. I'm happy to come back if you want me to come back and talk about this topic or others in more extensive format. Happy to do that for sure in the future. Yeah.
Thanks a lot for the words. Yeah, thank you for joining the talk.